Greetings, I'm Yvonne, staff for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. For astronomers and astrophysicists, this is a wonderful era. Advancements in telescope design and in data collection are producing many new discoveries, one of which is the diversity of planetary systems in the universe. Today's guest is Joan Najita, astronomer and head of the scientific staff for user support at the National Optical-Infrared Astronomy Research Laboratory, better known as NOIRLab. She's also a 2021-22 fellow at the Harvard Radcliffe Institute for Advanced Research. Dr. Najita's research focus is the formation of planets and planetary systems. And today she explains for us the conditions and ingredients that produce planets and planetary systems, as well as the surprising diversity of these systems. In addition to her research, Dr. Najita is involved in the development of advanced tools for today's astronomy. And importantly for us, she's a forceful promoter of science communication. We are most fortunate to have her with us today for a presentation on what astronomers are learning about planetary systems. Dr. Najita, welcome.
Thank you so much, Yvonne, for that extremely kind introduction. I will try to share my screen. Thank you so much again, Yvonne, for that kind introduction and for the opportunity to be here today. The work of Science of the Public is so very important to society and to our fast-changing world, and I'm delighted to be here. Hello, everyone. I'm Joan Najita from NSF's NOIRLab, and today I'm pleased to be able to share with you some recent developments on the diversity and origins of planetary systems. But before beginning, I thought I might mention a few details about the organization that I work for, NSF's NOIRLab, since it may not be familiar to many. So NSF's NOIRLab is the National Science Foundation Center for Optical and Infrared Astronomy. We're based in Tucson, Arizona, and we develop and operate facilities located in Hawaii, Chile, and Arizona, including the Kitt Peak National Observatory shown here. In addition to operating facilities, we also create and serve data sets, as well as the tools that can be used to analyze these data sets. And this is all in the service of the idea that anyone with a good idea should be able to pursue that idea using forefront research capabilities. And if you're interested to explore the universe too, I invite you to visit www.legacysurvey.org, where you can explore our own galaxy, the Milky Way, as well as galaxies beyond the Milky Way out there in the universe. But now to return to the topic that I was hoping to speak about on the diversity and origins of planetary systems. I thought I might introduce that topic by first describing the classic picture of planet formation that was created to understand the origin of the planets in our own solar system. Then describe some of the diversity that's found in the planets beyond the solar system, some of the new insights they provide, and examples of the open questions they raise. And then, if time allows, I also thought it would be fun to have a look at a different kind of diversity in astronomy, the diversity in how discoveries are made and the implications of that diversity for the development of our field and for our interactions with society. So beginning now with the classic picture of planet formation, as I mentioned, this picture was created to explain the planets in our own solar system, which, as you know, include Mercury, Venus, Earth, and Mars, the terrestrial planets, as well as the giant planets, Jupiter, Saturn, Uranus, and Neptune. And some of the questions that we have about the planets are, how are they made? Where did they come from? And whether the solar system is unusual or not, and why. We can get an important clue to where the planets come from, how they're created, by looking at where the planets are in the night sky. If we look at the night sky, we'll see that the planets are located in a line in space in a line on the sky, which is really a plane in three-dimensional space. So for example, here we have Mercury, Venus, Saturn, Mars, the Moon, and Jupiter all in a line. There's also a star shown here as well. But the planets and the things in the solar system lie in a line in the sky, which is really a plane in three-dimensional space. From that simple observation, it's perhaps not too surprising to imagine that the solar system formed in a flattened disk of gas and dust. By gas, we mean hydrogen and helium primarily. And the dust, it's not simple household dust, but ices like water ice, carbonaceous soots, and silicate ashes. Now you might be wondering, where can I find an example of a flattened disk of gas and dust that might be making a planetary system? Well, you may have already seen a planet formation environment, perhaps on a calendar page or a mug or a mousepad, because these images are very popular in astronomy. For example, here's one, the famous pillars of creation in the Eagle Nebula as captured by the Hubble Space Telescope. And deep in these big pillars are many examples of planet-forming disks. Another popular place to find planet-forming disks is this calendar picture of the Horsehead Nebula in Orion. And deep in these dark regions here, what are so-called externally irradiated molecular clouds, are other examples of planet-forming disks. So the question for planet formation is, how do we go from these flattened disks of gas and dust to make the planets? Well, the story that astronomers have come up with to explain this is an amazing tale extending over many, many orders of magnitude. And it goes a little bit like this. So we start with the smallest things in the solar system, micron-sized bits of dust that collide and stick and grow to eventually make centimeter-sized pebbles. The centimeter-sized pebbles get themselves together to make kilometer-sized planetesimals. If these planetesimals are icy and they see the star, they'll turn into these beautiful cometary shapes. But if they're not icy and they're more rocky, we end up with asteroids. These planetesimals collide and grow to make protoplanets the size of Mars or the Moon. And the protoplanets collide and grow to make things as big as the Earth. And we can keep going. Earth-sized objects can collide and grow to make the cores of giant planets that are maybe 5 to 10 Earth times the mass of Earth. And if these giant planet cores grow quickly enough so that they can begin to enrobe themselves in some gas, and they acquire a little bit of gas, they become an ice giant like Neptune. But if they grab a lot, then they can become a giant planet like Jupiter. So this theory, which is called core accretion theory, because we first create a core and then accrete a gaseous envelope, is a very popular, very enduring theory of planet formation. Because, for example, it can explain what we see in the solar system. We can explain the terrestrial, rocky terrestrial planets, as well as the gas giant planets. So it's very satisfying, very popular. But now let's see how well it does in explaining some of the new planets that have been discovered beyond the solar system. And let's begin by looking at the planets that have been discovered close to their central stars, say within the orbit of Jupiter. These planets have been discovered with a couple of different methods, the first one being the so-called radial velocity method. So in this one, which you may have heard about, we have a star orbited by a planet, and we can't really see the planet directly, but the planet exerts a gravitational influence on the star. It pulls on the star as it orbits, and it causes the star to do its own little dance, a small little wobble. Astronomers try to measure this wobble, and by making that measurement, we can infer how massive is the planet, as well as how far the planet is away from the star. And these observations might be made, for example, with a ground-based telescope, like the Wind telescope on Kitt Peak. So with these measurements, we can measure the mass of the planet and the distance that it's away from the star. Another technique that's really commonly used is the transit method. In this situation, we have a planet, a star, and the planet passes in front of the star. And because the planet is much darker than the star, it blocks out some of the light from the star. And the decrement, the decrease in the light from the star as the planet passes in front, is a measure of how big the planet is. If we measure this decrement a couple times going around, then we can also measure the orbit of the planet. In other words, how far it is away from the star. So with those kinds of measurements, we can measure the planet's size and the distance from the star. And with both of these methods combined, we can measure planet masses, planet sizes, and orbital distances. And now we're ready to make a plot. So for example, we could summarize all of these observations with a plot that has planet mass on one axis and distance from the star on the other axis. And for just to give some benchmarks, we could have the Earth here, Jupiter here, and Neptune here, based on their masses and positions in our own solar system. And now we can ask, with those observations made with radial velocities and transits, where do the new planets lie? Well, they end up here. So you can see that there are many planets discovered beyond the solar system that have masses much larger than any planet in our solar system. Many of the planets are much closer to their central stars than any planet in our solar system. And some planets have masses that we've never seen in the solar system. For example, these so-called super Earths, which have masses between the mass of Earth and Neptune, are very common. They commonly orbit stars out beyond the solar system, but we don't have any example of that within the solar system. So these kind of surprising and unusual properties may raise a lot of questions in your mind. And one of the questions might be, why are all these planets so much closer to their central stars than the planets in our own solar system? Well, astronomers, we like to work with what we know and to build on our knowledge or what we think we know. And so our current working hypothesis is that the planets really formed at much larger distances, more like where they are in our solar system. And they migrated in closer to their central stars through the action of other processes. This leaves, although that's a good place to begin, this leaves open many questions. Why are some planets so much more massive than the planets in our solar system? Why do we have planets that are not seen in the solar system? When did these planets form? What caused them to migrate? When did they migrate, and when and why did they stop? These are all important questions that astronomers are now wrestling with. These observations, though, also raise some interesting other possibilities. They point to the possibility of habitable planets around other stars, and that also raises questions about how well we really understand how the Earth formed. Because in analyzing the transit data, astronomers have inferred that something like 20% of stars like the Sun have an Earth-sized or Venus-sized planet orbiting at an Earth-like or Venus-like distance from their central stars. Now, if we wanted to know how common are solar systems like ours, or whether there are habitable planets out there, starting with 20% of stars potentially having these kinds of systems is a great place to begin. So we're pretty excited. But I wonder whether we really understand what we're discovering here, because this high frequency of Earth or Venus-like planets around other stars seems to be in some serious tension with our understanding of how planets like the Earth formed. To think about that, we can go back to our story of Earth formation. And it's actually quite a violent and catastrophic story. And the reason is, if we think about our picture, that in order to go from a Mars-sized object up to an Earth-sized object, which is 10 times more massive, basically we have to smack 10 Marses together in order to get there. Each of those collisions is expected to be quite catastrophic and to generate a lot of debris and dust in the region where the Earth is forming. So for example, when these collisions occur, parts of the planets are broken off and and into shards, into debris that then grinds itself down back into the small dust grains that we started with. And so the expectation is that we would have a big ring of debris in the vicinity of the Earth's orbit. And this debris sees the star, it's heated and illuminated by the star, and it'll glow in a big hot ring. Now the emitting area of that ring is very large, the size of the Earth's orbit compared to the size of the Earth. And so the emission from this big hot ring of dust is expected to be the most visible signpost of the formation of Earth-like planets. And that's basically the problem. Because if 20% of stars like the sun form Earths at the time and in the time we expect, in the way we expect, then when we look at those stars of those ages, we should expect to see 20% of them having this hot dust signature of Earth formation. But in fact, only something like 20% of stars, although 20% of stars should look like this, in fact, only a few percent really do show that signature. So where are the dusty footprints of those other Earths that are forming? This is a really interesting question, and that I originally thought about in working with Scott Kenyon at the Center for Astrophysics here and Ben Bromley at the University of Utah. And some of the potential ways in which this problem might be solved are really quite interesting. One possibility is that our theory is wrong. Even though we love core accretion theory and it's been so successful, could it be that some part of that theory is wrong, that Earths really don't form that way? Or that would be a little sad because we love core accretion. Another possibility is that maybe the observations are wrong. And although we would really be happy if something like 20% of stars like the sun were forming Earths and potentially habitable planets, maybe there really aren't as many Earths out there as we think. So this is a really interesting tension, and the options are both really interesting. And this year I hope to return to this problem and try to investigate what might be going on. So I hope this gives some idea of the planets that have been discovered close to their stars, the kinds of questions they raise, and what they might be telling us about the understanding of the formation of our own solar system. But now let's have a look at some of the even more recent results that people are finding, astronomers are finding, about the possibility of planets located very much farther from their central stars than any planet in our solar system, at the orbit of Neptune and beyond. Now, whereas the planets that were discovered close to their stars were made with observations of telescopes that work at optical wavelengths, the wavelengths that our eyes are sensitive to, the planets discovered very far from their stars are actually made with radio telescopes. And the most popular, the most powerful one of this kind is the Atacama Large Millimeter Array, located on the Chajnantor Plateau in Chile. ALMA is a collection of radio telescopes that, working together, can synthesize high sensitivity, high angular resolution observations of the universe. In other words, it can discern very fine details. This is an extremely powerful new capability for astronomers. And when ALMA decided to make its first high angular resolution observations of the universe, it chose to look at a planet-forming disk. And this is what it saw. Luminous rings of emission interleaved with dark gaps. So nested rings on the size scale of the orbits of the giant planets in our own solar system, but also extending to much larger distances. Not only was this a surprising and actually quite beautiful image, it was also exactly what astronomers expected to see. How often does that happen? Because if you'd asked astronomers in the decades leading up to this image being produced, what would a planet-forming disk look like? We have many artist conceptions of this, and they look like this, where a planet clears out a dark ring in the gap in the vicinity of its orbit. And if you have multiple planets forming, you would have multiple nested rings. And that is exactly what ALMA saw. So of course, astronomers have been very eager to keep going, and many other images have been collected, and they also show something very similar. Many rings and gaps. Sometimes the rings are very thin, sometimes they're thicker, sometimes they're even thicker than that. If you look closely, sometimes you can also discern very fine spirals as well. But as you can see from this collection, the most common sort of structure are these rings and gaps. And because that agrees so closely with what we expected to see, astronomers have been very quick to try to infer what kinds of planets could be forming in these disks. And this is what people currently think. So looking at our plot that we made before of planet mass versus separation from the star, distance from the star, here again is Earth, Jupiter, and Neptune. These gray dots are the planets close to their central stars that we discussed earlier. And these colored points here are the planets that are inferred from the images of the formation environments, those rings and gaps. And you can see from this plot that some of these planets are much more massive than any in our solar system. Their masses extend down to the mass of Neptune and below. And they orbit at distances much larger than the planets in our solar system. It's a little hard to see that actually from this plot, because this is on what's called a logarithmic scale, where the distances are all squished together. But just to give an idea of what this is really saying, schematically, if these are where the planets in our solar system are located, the rings that Alma sees are out here, and they may be indicating that planets are present here. In other words, that planetary systems may be much more diverse than we had imagined. But that's not the whole picture, because although ALMA does measure these really big disks with the rings and gaps, many of the disks that it observes, have much more compact structures. And so this raises a couple of questions for astronomers. Of course, we're all concerned and curious about whether these really are the footprints of planets. And a lot of effort is going in by a lot of astronomers to work on that question. But we might also ask, what's the relation of all these beautiful images to us, to the origin of the solar system? In what kind of disk, any one of these, might the solar system have formed? And do any of these disks look perhaps like what the solar system once looked like in its infancy? We can answer a question like that by starting with an image from ALMA and evolving it in a computer to see whether we end up with the solar system. In other words, let's say we start with an image like this. This shows us where the pebbles and planetesimals are located. We can put the pebbles and planetesimals into a computer, let them collide and grind down and create a lot of debris, starting with this image at 1 million years and letting that collision and debris process occur from tens of millions of years to billions of years. And after all that time, see whether they could produce the solar system, which today, at 5 billion years of age, really has very little debris and very few solids. That's one way to do it. But we also know that you can start with a lot of different kinds of disks, not just one. And so a better method would be to start with many different possibilities and not just let things grind down and wait to see what happens, but to use all the observations that astronomers have collected of stars of different ages from tens of millions of years to billions of years, and make sure that what we think is happening really agrees with what happens in nature. In other words, let's start with a whole bunch of different possibilities, let them collide and evolve, and make sure that the way that things work really agrees with all the observations astronomers have made of the sizes of the debris that's seen at these very large distances, the brightnesses of the debris, and how often the debris is seen. And by constraining the evolutionary paths in this way, we could then ask which paths lead to the solar system. This is a project that I've also been working on with Scott Kenyon at the Center for Astrophysics and Ben Bromley at the University of Utah. And the results so far seem to indicate that disks have two distinct kinds of life histories. Disks that are born big live spectacular lives, When they're young, they have these big, bright structures that astronomers love to look at. And as they age, they produce all the spectacular debris that astronomers love to study. They are perennial favorites, the attention-grabbing stars of the show. In contrast, disks that are born small, they never do anything so demonstrative. They don't produce this kind of debris, and instead they live much tidier, quieter lives, eventually evolving to solar systems like ours. So these two kinds of disks, big and small, present two very different faces to the universe. To an interstellar traveler, perhaps equipped with radio or infrared eyes, the big disks are fantastic tourist attractions. At 1,000,000 years of age, they have the intricate rings and gaps, potentially these spirals that attract our attention. And if you miss the show in the first 1,000,000 years, that's okay, because they're spectacular throughout their lives. From tens of millions of years to billions of years, they have these bright, glowing rings of debris, like perennial bright neon signs inviting passersby to come in and take a closer look. The smaller disks are hardly noticeable in comparison. Without even a porch light on to attract any attention, we'd be very tempted to just pass them by on the interstellar highway. So these results and these kinds of observations give us some new insights, help us to answer questions about our origins, and give us some insights into where to go next. Because although we'd be tempted to overlook these smaller disks, it looks like these are the ones that are most likely to hold important clues to our origins, and they're certainly worth a closer look. So it'll be fun to see what astronomers find when they do that. So I hope this conveys some of the excitement over the new kinds of planets that have been discovered, the insights they provide, the questions they raise, and sort of some of the methods that astronomers use to address these kinds of questions. It's a really exciting time for this topic, and I'm really so grateful to the Radcliffe Institute to have the opportunity to work on these kinds of topics this year. As it turns out, though, this is also the year of the 2020 Astronomy Decadal Survey. Yeah, it's an important year for the astronomy profession in general, because it's the year in which the results of the 2020 Decadal Survey in Astronomy are being reported. The planning exercise where the astronomy community gets together to think about where it's going and to make recommendations to our federal funding agencies, NASA, the National Science Foundation, and the Department of Energy on funding priorities. So in that context, I thought it might be fun to have a look, to chat a little bit about another kind of diversity in astronomy, kind that I've also been thinking about, the diversity in how discoveries are made in astronomy, and what are some of the implications of that diversity for how we meet our commitments to society and plan for the future. This is a really big topic, and I really can't begin to address it in any great detail in 5 minutes, but I hope I can convey a sense of how the argument goes by inviting you on a quick tour of some recent major discoveries in astronomy. So let's have a look. So thinking now about discoveries in astronomy over a pretty short period of time, from 1993 to 2005. And just to make it quantitative, these are all discoveries that are prize-winning kinds of things. In this short time period, we learned that the solar system was even more interesting than we originally thought, because it doesn't end, the solar system doesn't end at the orbit of Pluto, but in fact, the solar system actually retains a pristine belt of planetesimals beyond the orbit of Pluto that holds precious clues to the origin of the solar system and to our understanding of planet formation in general. Also in this time period, we learned that the solar system has a lot more planets than we thought. There are a lot more planets that are like Pluto, and that planet formation yields many more diverse kinds of planets than we previously had considered. Also, in this same time period, exoplanets were discovered. This was only actually about 25 years ago, and today it's one of the hottest topics, if not the hottest topic in astronomy. And this discovery really opened up the question, our ability to begin to address the question of whether we're alone in the universe. Also in this time period, astronomers took a close look at the stars orbiting near the center of our galaxy, and they found that those orbits could only be explained by a very dark, very massive object with a mass millions of times the mass of our sun, a supermassive black hole. And these observations confirmed that those kinds of objects really do exist. Also, in the same time period, we learned there was the discovery of dark energy, which addressed the question of what the universe is made of and illustrated that we know even less about the universe than we thought. Because everything that we know in our daily lives, ourselves, our pets, our food, the earth, gas and dust in planet-forming disks, all of that makes up only a small fraction, maybe 5% of the universe. Even before dark energy was discovered, we already knew that there was something else much more than this so-called baryonic matter in the universe. For example, what's called dark energy, or dark matter, which makes up a much larger fraction than baryonic matter. But the discovery of dark energy showed that there was a component of the universe that made up even much more of the universe that we also don't know anything about. So indeed, we know less, we know less than we thought, and there are some new important mysteries to contemplate. These kinds of discoveries, these kinds of astronomical discoveries provide us with perspective about the nature of the universe we live in, what's in it, how we got here, and how we fit in, our place in the universe. So what did it take to make these kinds of discoveries? This table shows the examples we were just talking about, the groups that made those discoveries, and the resources that were used to make them. You can see that the last two examples we talked about, the black hole at the galactic center and dark energy, were made by large teams of astronomers, sometimes working with the most sophisticated resources available today, and other times working with a wide variety of resources, from very modest to very complex. But the first three examples that we discussed were actually made by very small groups of astronomers working with very modest resources. So what are some of the messages of this simple tour? I think it illustrates in a way how, although astronomy is one of the oldest sciences, it's also very youthful, with major discoveries made often and in very diverse ways. Today in science, a lot of the focus goes to the efforts of large teams, with the idea that large teams are critical to making discoveries and maybe the only way to make discoveries. But our own data, our own history, shows that many major discoveries are actually made by small groups and individuals. Also, if you read the news or planning documents, you may hear the story that state-of-the-art resources are absolutely critical to continued progress in science. Only by having the biggest machines, the most expensive machines, can we continue to make discoveries. And that might worry you because the cost of these machines is growing all the time. But our own data, our own history shows that even very modest resources, you can make major discoveries with only very modest resources. Perhaps those that are made available to groups with novel ideas or passions, those who are willing to take big risks with the potential for big rewards. And while discovery in astronomy is in fact, yes, driven by technology, there are very strong human elements to how that works. The curiosity and passion that people bring to exploration and discovery are critical, as are new ideas, diverse perspectives, and simple human elements like sometimes extreme persistence. So what can we take away? For me, the diversity of discovery pathways that are open to us make me very optimistic about our ability to continue to contribute to society, astronomy's ability to continue to contribute to society. But by providing that perspective on where we've come from, where we're going, how we fit in the universe, it also, the diversity of discovery pathways also suggests that we'll have a lot of flexibility in responding to new kinds of challenges that may come up. But where we can compromise is with people and opportunity. We need to continue to provide people who come with their different ideas and perspectives and skills the opportunity to engage in the enterprise of discovery, because that's in fact where much of our discoveries come from. I hope these are also the priorities for the 2020 Decadal Survey in Astronomy as it's actually implemented. But on a personal level, and along the lines of opportunity, new challenges, and continued discovery, this year at Radcliffe, I have the great fortune and privilege to work with two exciting groups, two amazing groups of Harvard undergrads. And so I just want to let people know about that. And so with Gabriel and Josh, I'll be exploring our own galaxy, the Milky Way, using an exciting new data set. And with London and Andres, I'll be looking into an important science and society issue. My sincere thanks to these students for their incredible enthusiasm and insights. They're all really so inspiring. And with that, I hope that gives some of the sense of the issues that I'm currently thinking about, also a sense of how astronomy progresses more generally, and an idea of the kinds of contributions that astronomy makes to our understanding of how we got here, where we're going, and our place in the universe. And many thanks again to you, Yvonne, for the opportunity to share these ideas today.
Thank you so much, Dr. Najita. That was a most interesting presentation, and I especially appreciate your kind of encouragement for, say, young people to get into this field, that there are many opportunities and there are many ways to make these discoveries. That was very interesting too. I very much appreciate your giving us your time, and I hope you have a wonderful year this year at the Radcliffe Institute, and I'm sure it will be very productive. Again, thank you. Bye.